examples of classical field theories. And there are two motivations for it. Firstly, it is a very beautiful subject by itself, and in fact today we will see glimpses of what could be one of the greatest unifying concepts in physics, something called spontaneous symmetry breaking. And concepts like this you get in field theory, which in some sense has no analog when we work with relativistic particles. Because if you remember, the way we started with was that we started with the path integral for a relativistic particle and we found the propagator. Then we said that this propagator tells you that there is an underlying field description for the system, and then we obtained that field description by creating and destroying particles from the vacuum and writing down a vacuum to vacuum or vacuum persistence amplitude or a vacuum to vacuum amplitude. Then we did a Fourier transform of that, which led us to an action. If you remember the previous analysis, that the action which we found had the form which was, for the simplest case of a scalar field, it was half integral d4x dA of phi minus m square phi square. This is the action we found, and then we said that we can study this field itself. But at this level, if you study this, you are essentially end up going to get this propagator which we started with, which is all great fun, and you will discover a few more things like the 0-point energy, etc. But nothing substantially new happens. But it turns out that we can think of this as a prototype of an action in field theory, where we are thinking of something like integral over d4x times some Lagrangian L, which depends on dA phi quadratically and on phi in some particular way. Here it happens to be quadratic in phi as well. So this is a more general structure which we are going to explore. And it turns out that depending on the nature of the Lagrangian which I write down here, all kinds of strange things can happen. Not all of which are easy to understand in terms of the particles and interacting particles. So the field theory sort of acquires a life of its own, and that doesn't happen in this kind of a field theory. If this potential is just quadratic with a minus m square with a real m, it's called a free field theory, which essentially corresponds to relativistic particles, and the distribution relation is just omega square is equal to k square plus m square. Okay? Nothing very interesting happens there, anything more than this. Except, as I said, there is something called 0-point energy which we will come back to when we quantize it. But the moment you look at more non-trivial Lagrangians, all kinds of beautiful things happen, so which is what we want to explore today. So the way we are going to do this is, I want to do first real scalar field, which is what is here, this phi is a real function. Then we will do a complex scalar field, and then we will do electromagnetic. That is the order, and then we will discuss the quantum theory of each one of them. So let us start with this. So here I want to let us first finish this off. This case is absolutely trivial. So you have a
So okay, I'm probably asking something beforehand. So when you start with the field theory, and you want to relate to the interpretation in terms of particles. You actually
not always.
I mean, suppose
I'm now just going to study.
Yeah, talking about the free field theory and the way you.
Right, free field theory it is. You want to connect with relativistic particles. Yes.
Correct. So the only way, I mean, so to relate it, you have to specify the fact that okay, you want to calculate the time order product of the.
No. All those will come when we do the quantum theory. So wait for 3 more lectures. Okay, that will all happen naturally. So that we will do later. But right now I am only going to study classical field theory of a Lagrangian L, which is more general than this. So this is a Lagrangian which involves dA of phi and phi, and let us just look at that system first. So the specific case of a Lagrangian would be this, where it is just quadratic, and let us finish that off first. Okay. So you have the entire formalism for the Lagrangian and how to deal with it I have already developed in the last lecture for the most general case of Lagrangian. Okay. So the first thing you would like to do is to find what is the canonical momentum for the field, which is by definition dl with respect to d of dA of phi. So which if you differentiate, you have one half factor going away and you will end up getting dA of phi. In particular, the important quantity which we want is the pi 0, which usually in field theory books would be just denoted as pi. Okay. So that pi 0 is the zeroth component of this, which is just phi dot, which of course is a function of t and x. Okay. Now once you have got that, you can write down the expression for TAB, which is, in this particular case, it is pi a, which is dA of phi, dB of phi, minus delta AB times the Lagrangian. So this is pi a, this is dB of phi, this is like p q dot minus L, which again we discussed in the last lecture. So this is the structure which you have. So let us look at the 0 component of it. With the signature which we are using, it doesn't matter which one we are going to look at. So let us look at T00 for example. So if I look at T00, you are lowering this, so you get a phi dot square, then minus the Lagrangian. So let us look at this Lagrangian again. This Lagrangian, if I expand it out, okay, let me write it down. If I expand it out, it is half. Inside it there is this structure. That is going to give me phi dot square minus del phi the whole square minus m square phi square. So when you work this out, this half nicely cancels with this term and you get a half phi dot square plus del phi the whole square plus m square phi square. This is the quantity which one would have called the Hamiltonian density, and the integral of that over all space would have been the Hamiltonian for the system. Okay. Now there are a few things which you can look at it. First of all, it is sort of gratifyingly positive definite, so that the energy is not going to go negative on you. And if you look at the structure of this, you find that it costs energy to increase the amplitude of phi. That is to be obvious. Okay. So in fact, if you don't have this del phi square, this is like half phi dot square plus m square phi square, which is like a harmonic oscillator. So the m should be thought of as essentially something which is going to give you in the solution something like e to the imt, e to the plus or minus imt, like e to the plus or minus I omega t of the oscillator. So this tells you that this is like a quadratic potential and it costs energy to lift it away from phi is equal to 0. This is a new phenomenon. This tells you that if the field has gradients, that is if the field is wiggly on this space, that also costs energy. So since systems in some sense you can find the dynamical equations for systems essentially either using an energy concept or the action concept, you can think of it that it is going to first of all trying to reduce from some non-trivial value of phi to phi is equal to 0, which is exactly what a pendulum would do. You lift it up and the harmonic oscillator will come down to the 0, but by that time it has acquired a velocity, so it will overshoot. In the same sort of way, even in space, if you give it a wiggle, it is trying to minimize the wiggle, so it will come down in the gradient, but then when it does that, it will overshoot. And this is what gives you the spatial oscillation, and this is essentially why waves propagate. Okay, but there is a physical picture of that. There is something which is happening here only in time and in phi, but there is also this gradient term which is going to minimize the gradients of the field. But of course, it never succeeds, just like the pendulum never comes to rest if it has a finite energy. So this is what the Hamiltonian is going to tell you. And all these concepts, just keep in mind that if I just replace m square phi square by a v of phi, see, which we will need later, and I don't want to rewrite all the formulas. Suppose you have an arbitrary V of phi. Okay? So since the algebra never touches this part of the system, all these results will continue even there. So instead of this m square phi square, you would have ended up getting plus V of phi. So as long as V of phi is positive definite, this is going to again give you a positive definite energy density and the Hamiltonian, etc. Okay? Fine. Now I want to spend a little bit of time on how to get this TAB for a more general system and how to write this entire thing in curvilinear coordinates. Essentially, it will also tell you how to do it in curved spacetime, but we are not going to do curved spacetime in the part of the course, but this is something which you should know. What we have done here is to obtain a TAB with a pi a and dB of phi, and I told you the other day that there is no guarantee that this is going to be symmetric. Okay. In this particular case, it happens to be symmetric because this quantity, the pi a is just dA of phi, but in general it is not guaranteed. But there is a way of getting a symmetric energy momentum tensor from a Lagrangian by a procedure where you vary the metric in this space. Okay. So I want to, since most of you might not have done any GR, I am going to spend a little bit of time trying to introduce what it means. Now what it means turns out again to be very elementary and something which you guys have all learned in different contexts, but it is never taught in that particular way. Suppose you look at the line element in Cartesian coordinate. For a moment, let us forget space-time and come back to ordinary space. So this is the length interval between x and x plus dx, y plus dy, z plus dz. So if I do the same thing in polar coordinates, that is, I go from the coordinate system x, y, z to r theta phi. Okay?
That term is z in the last.
Oh, yes. I don't want 2 ui square. Yeah. If I do this coordinate transformation, then I suppose you all know this, that dr square plus r square d theta square plus r square sine square theta d phi square. You also know how to obtain this, that is, you take dx, dy, dz in terms of this, plug it in and you do the maths and you will end up getting this, right? So this is a general coordinate transformation from one set of coordinates to another, and this is completely nonlinear, and in fact it is a crazy transformation. Even the dimensions of this are not length. R is length, theta and phi are not length. So it is not even necessary that coordinates should always have dimensions of length. It will all take care of itself. When you write this down, this r square will take care of that. Okay? So you can write down any kind of general coordinate transformation of this kind. And suppose we do this in 4 dimensions, and what happens? So in order to do that, it is nice to write things down in a slightly more sensible way. First of all, from dl square, okay, so here itself let me indicate that. So I could have written down this dl square as delta alpha beta dx alpha dx beta. Okay. So delta alpha beta is the normal Kronecker delta function, and this is going to reproduce this quantity for you. But what does it become here? This one is going over to something which I will call g alpha beta dx alpha dx beta in some new coordinates. So let me put a dx bar here. So x, y, z is one set of coordinates, and this is going to be x bar, y bar, z bar. Okay. So I am going from x, y, z to x bar, y bar, z bar by the standard transformations, and this quantity will go into this g alpha beta. But how could I have found the form of g alpha beta? Again, it is quite simple. You start with this expression and you say that dx alpha is going to be dx alpha with respect to, let us say, dx bar mu, dx bar mu, with a summation over mu 1 to 3, right? Then you plug it in here then this eta alpha, this delta alpha beta times this and another copy of that is going to determine for you what G alpha beta is. We can play this entire game in 4 dimensions. So in 4 dimensions, you will start with a ds square, which is eta ab dxa dxb. And you do exactly the same kind of transformations. xa goes to some x bar a, which are functions of xa, some general coordinate transformations. And then you will find that this is going to be GAB, which will depend on coordinates dx bar a, dx bar. This is x bar. Just as in this particular case, x bar, y bar, z bar was r theta phi, and these metric, once I have transformed these coefficients, this is g theta theta, right? So this quantity is, there is a g r here, which is 1. So this quantity here is g theta theta, which happens to be r square, and similarly d phi phi is r square sin square theta. So in the same way, you will get some GAB of x bar here. It just turns out that in general, if I write down a metric like this in 3 dimensions, or even in 2 dimensions, or write down a metric like this in 4 dimensions, this is not something which you obtain by coordinate transformation from another space with Cartesian coordinates, but it essentially represents a curved space geometry. So this is very clear in 2 dimensions. So 2 dimensions, suppose I have written down a metric d theta square plus sin square theta d phi square. This is the surface of a sphere. Okay. While if I write dr square plus r square d theta square, that is just a plain sheet of paper in polar coordinate. So in general, this represents a curved geometry, but we don't need to worry about it. But this is the way you will write down a metric in arbitrary coordinate system. Now, if you have an expression for Hamiltonian or energy or action or whatever, and suppose you had it as some integral dt, dx, dy, dz, you may want to do this in spherical polar coordinates. Then you change x, y, z to r theta phi. What will you do to dx, dy, dz? You will change it into r square sin theta, d theta, d phi times dr. Right? Now, where does this r square sin theta come from? The r square sin theta comes from the determinant of this metric. If you take the determinant of this, you are going to have a 1 r square and an r square sin square theta. The product will be r4 sin square theta. Root of that gives you the metric. That is something which is very straightforward to prove, which I would let you do that. The Jacobian of this transformation will essentially be square root of g. Now, in this particular case, the determinant is going to be negative because it is minus 1, minus 1, minus 1, minus 1. So sometimes you write it as minus g, but it really doesn't matter. Okay, either root minus g, or I will think of it as root g with the understanding that your determinants are defined with a modulus on it, so it is positive. Okay, so how does this Lagrangian or the action I wrote down transform to an arbitrary curvilinear coordinate? That is also easy. So I want to write down the action valid in any coordinate system, so that when I change my coordinates, the action remains invariant. So what I will do is, first of all, I have an integral, and originally I had an integral over d4x. But d4x is a good measure of integration only if it is Cartesian, dt, dx, dy, dz. But if it is in general, I need that determinant of the metric. So I will write it as this into root g. Okay? Most books would write it as minus g, but as I said, by my convention, I am not denoting it. Okay? This is what you have. Or maybe you will go and read other books, so let me put a root of minus. Okay. Right? So incredible though it might seem. Okay, so this is your volume element. Then you want to write down the rest of the action, that is Lagrangian. So it has a half. Here I had a dA and a dA. How did we obtain that? Essentially, this is obtained by using eta AB dA of phi, dB of phi. Remember that this dA symbol stands for d by dxa. This is a primitive object. X with the superscript a is your vector. Okay? So d by dxa is a primitive object. You don't have to touch that. And there are two such things. And then you have to put a eta ab. What is this eta ab with upper ab? This is the inverse of the matrix which you have with eta ab at the lower indices. So you need to find exactly that. So just as you have got a GAB, you find a GIK such that GIK GKL is the Kronecker delta. So if you think of this as a matrix, this is the inverse matrix for that. So this is a definition of this quantity. Once you have got that, you go and plug that in here. It is GAB, dA of phi, dB of phi. Then you have a potential term which was minus m square phi square, which I will just write as minus v. So this is the action in an arbitrary coordinate system, which is how I introduced it, but it is also valid as a valid action in curved spacetime. So if you are doing quantum field theory in curved spacetime later on at some stage in life, this is the action you will be working. Okay? Now let us try to understand this a little bit in greater detail. Originally we had only one function in the action, which is phi of x. But now I have got a couple of them. There is also this phi and a GA. So if you give an action to a physicist, the first thing he will do is to vary it. So normally we would have varied it with respect to phi a, and that would have given you the field equations. But you can ask another question. What happens if I vary it with respect to GA? Just for fun, what will it give? Okay. What should it give? We are looking for the variation. Since you already done functional differentiation, you are essentially going to do the functional derivative of a with respect to GAB. So we are going to just vary this with respect to GAB. So you can I will write it down and explain it. It is usually written in this form. Okay, so let me explain this. This is the variation with respect to G. So it is of course going to have delta GAB times some quantity. What should that quantity be? Since there are two indices here and this is index free, you need two indices on that. Further, since this is symmetric, that should also automatically be symmetric, because the only symmetric part will contribute. If it had an antisymmetric part, that will anyway go to 0. Then this should be also a covariant object. If you make an arbitrary coordinate transformation, nothing should change. Nothing is changing here. Nothing is changing here. This is to be covariant. That means the volume element which I write down should also be covariant. Of course, I could have absorbed this root minus g into this, and that would be a little bit crazy, because then it wouldn't have a nice transformation property. Right now, this has a nice transformation property. It goes to itself. d4 of x bar root minus g bar. Okay. This also goes to itself, and this will go to itself. So everything will transform appropriately. So this is the definition of a quantity, a second rank symmetric tensor, and this is identified with the energy momentum tensor. Now the question is, why should it be energy momentum tensor? Okay, that I cannot give you a complete proof, but let me just explain to you why that comes about. Eventually, when you do general relativity at some stage, you will have the action for a gravitational field plus the action for matter. And you will vary this entire action with respect to the metric tensor, which is like the gravitational potential, in order to get the field equation. When you do that, there is an action for gravity that you vary, and that will give you something like del square phi, okay, for the gravitational potential. Then you are going to vary the matter action. Suppose there is a scalar field which is producing the curvature in space-time. When you vary the matter action with respect to GAB, it will produce something, and this is going to act as source of gravity. And by definition, the source of gravity is the energy momentum tensor, because essentially energy and mass are the same, and mass is what produces gravity, mass density is what produces gravity in Newtonian physics. Okay? So this is a good way to identify the energy momentum tensor. As a bonus, we get something which is symmetric. So let us try our hand on this. take this action, vary it and see what is TAB. Okay. So we wanted to vary this object. It looks simple enough except for the fact that there is a root minus G which I want to vary. So I need to know what is the variation of determinant of a matrix if I vary the elements of the matrix by a small amount. Okay. The matrix here is the one with GIK lower, because my original starting point was this. This is what I am going to identify with the matrix M. So this quantity will appear as the inverse of the matrix. But here we want actually the variation of that. So we need to know how to relate these two. That is very easy, because from these arguments you can show that whenever there is a delta of the upper quantity or delta of the lower quantity with a contraction, one is the negative of the other. Because if I do the delta of this quantity, that is going to be 0. So that is not an issue, but let us first do the variation with respect to the lower index MIK. So here we will again use the same result which we had before, that the determinant can be written as exponential of trace of log of m. This is the same as saying log of determinant of m, which is log of products of eigenvalues, is trace of log m. So if you do this, first delta of any exponential is going to give exactly the same thing, so that is just determinant of m. So the exponential is taken care of. Then I just need to do delta of trace of log m. Trace is a summation, so delta flows through that. So trace delta of log m. Delta of log m is 1 by m delta m. 1 by m is m inverse. So m inverse delta m. Okay. So we get the result applied to G. Delta G divided by G, this is delta of determinant divided by this determinant, is equal to trace of M inverse is G some A B, okay, A K, then delta is going to be delta of G K B. Trace tells you that in this matrix you identify A with this and you remove this and you sum over. Okay. Now you write this delta, this is going to be on the left hand side, it is delta of log G. It is good to write this since we need root minus G as root minus G square. So log of something square is 2 times log of that quantity. So this is going to be 2 delta of root G divided by root G. Therefore we get the result that delta of root G or root minus G is half, this 2 goes and sits at the right other side, square root of G, this is from this, then I have a G AB delta G AB, which is also the same as minus half root G G AB delta of G superscript. That is because this quantity is minus of this quantity, since the total delta of this has to be 0. Right hand side is either 0 or 1, so the variation of that vanishes. So this is the result which we will need. Delta of root G is minus half times this quantity. Okay. Now let us go and plug this into this and see what happens. So we want to vary that quantity. So you have the action which is integral root minus g d4x times the Lagrangian, and you are going to vary that whole quantity with respect to GA. Okay, so I get delta A to be equal to d4x I keep L and vary root G. That is something which we have done. So you end up getting minus half root G GAB delta GAB, the whole thing times L. Or okay, this is L. Okay, this is the one term. Then I had to get a variation from this L. So what is that? That is going to be, I have a root G sitting there and I am going to vary L with respect to GAB. So let us look at L. L is this quantity. There is no GAB here, so there is only one GAB here, which is going to be half dA of phi dB of phi delta G. So let us get them all together. So we get delta E equal to, take a half out and integral d4x, keep the root G, and also let us keep a delta GAB, and let us see what remains. So I have taken the half out, I have taken the root GAB out, this quantity is out, so that gives me just dA of phi dB of phi from this. Then in this, once I have taken all of them out, I am going to get minus GAB. Yeah. So if you look at the definition of TAB, it is half this volume factor TAB delta GAB. So you have exactly that here. This allows you to identify this quantity as TAB. It's a little bit of an overkill for a real scalar field, but we will find that the moment we come to electromagnetism, as simple as electromagnetism, this is the fastest route to get TAB. Okay. Otherwise, you will end up getting an expression which is not symmetric, and you have to go around symmetrizing. So this way, you know what is the correct symmetric energy momentum tensor, and the canonical approach will give you another energy momentum tensor. And if you are interested in knowing what is the difference and whether it has any physical meaning, etc., there is some way it can be interpreted in terms of the spin density. Then you have two things in your hand, and you can subtract and work. Okay. So I thought I should illustrate this for you, and that was the first aspect. The second thing which you can do now that we are at it is to write down the field equations. Okay. What is the field equations which emerges from this action? So the field equations again we have done before. It is going to be dA of pi A, right? So pi A will be the derivative of the Lagrangian with respect to the derivative of the field. So if you do that, you end up getting here. So you are going to take the derivative of that with respect to the field derivative. So there are two factors of this. One of the halves will go, GAB will remain, and one of these quantities will go. So you will get dA of GAB. Let me write it in the conventional way. Root G GAB dB of phi. Root G comes from this, or root minus G GAB dI of phi once I had differentiated with respect to gravity. So derivative of this is equal to derivative of the Lagrangian with respect to the field, which is just V prime of phi times root G. So this root G again comes from here. Root G, then there is a V, it is the derivative of V which we are computing with the minus sign. So this can be written in a nice way as 1 over root G dA of root G GAB dB of phi equals minus V prime of phi. This is what the field equations will look. If we now go back to ordinary eta AB, then this is eta AB, this is 1, this is 1. So what you end up getting is dA of phi, which is box phi. So this is the generalization of a box to either curved spacetime or curvilinear coordinate. And this is something which all of you have seen, but it probably was not written down in this form. When you do say Schrodinger equation for a hydrogen atom, you have to write down del square in spherical polar coordinates. So del square is just box in 3D, right? It has 3 sides while box has 4 sides. So it is del square is just box in 3D. And the way you would have written it down is to write 1 by r square d by dr, r square d by dr for the radial part. So where is this 1 by r square and r square coming from? They are coming from root minus g, because g r up is 1. And you do exactly the same thing for other quantities, you will end up getting the entire Laplacian in 3 dimensions. Except that this can be used for anything you like. So this is something which you are familiar with, even though it looks unfamiliar. So this is your box. And if you are looking at it in the ordinary spacetime, we have got box of phi plus B prime of phi equals 0, which is your field equation. Going one step further, if V was just half m square phi square, this is going to give you the equation which is box phi plus m square phi square m square phi equals 0. This is the so-called famous Klein-Gordon equation. It is called Klein-Gordon equation because it is discovered by Schrodinger. That is the way we name things in high energy physics. And of course, Schrodinger already has another equation named after him, so it can be confused. So this is the expression. Now I don't want to go into too much of detail on Klein-Gordon equation because this is something which you would have either done in a previous course or you can read it up in any textbook. So I am not going to spend time, except a couple of comments about the solutions to that. How do you solve this? Okay, how do you solve this equation? Now the easiest way to do this is again to go into the Fourier space. So suppose you say that I take away the spatial part of the scalar field by saying that I am going to take phi of t comma x as integral some q of k key e to the I k dot x d3k over 2 pi the whole. Then when you expand this out, you are going to get a phi double dot minus del square phi plus m square phi equals 0. Right? So you operate on this phi with these. This goes for a right, so m square goes and sits inside. The double dot will give you a q double dot. The del square when acting on this will produce a minus k square, but there is a minus del square, so it will become plus k square. So this will, if you plug this in, this will lead to the equation qk double dot plus k square plus m square qk equals 0, and this is what we have always been calling as omega k square. So the solutions are just qk equals something e to the minus I omega kt plus something else e to the I omega kt. Okay, so these are two constants. So just for convenience, it will be called as alpha k. This should be called beta of minus k for convenience, but I will just call it beta of k for the moment. Okay, or let me actually call it beta of minus k, just for convenience. So you have this solution, and you go and plug it back into this to find the general solution. So the general solution is d3k over 2 pi the whole cube e to the I k dot x, and you substitute for qk of t. Qk of t is going to be alpha of k e to the minus I omega k of t plus beta of minus k e to the I omega k of t. So the first term can be written rather nicely as d3k over 2 pi the whole cube times alpha of k e to the minus I k x in 4-dimensional notation, because there is a minus I omega t plus I k dot x. Here you find both of them are coming with plus sign. This is why with some foresight we have put this. Here we will flip the sign of k, so this becomes plus k. This doesn't change anything, but this will come with a minus sign when I change that k. So that can be written as plus beta of k e to the I k x. Okay, so let us pause for a minute and ask what have we done. First of all, we have solved the Klein-Gordon equation in the most general context. I mean, this is why free fields are nice, and that is why free fields are completely uninteresting and dull, because the most general solution to it can be written down immediately. Okay, there is no dynamics really involved in it. What does it give you? It gives you all the time and space dependent parts are contained in e to the minus I k x and e to the plus I k x. These are running waves, and in normal language, I would have thought of this as positive energy solution. These are the positive energy solutions, and these are the negative energy solution, because omega k comes with a flipped sign. So you will have this equation which has a second order in time. If you did the same thing with Schrodinger equation, you will only get first order in time. You can play the same game with Schrodinger equation. You just replace this by some I d psi by dt, and then this m square phi is just some potential, okay, harmonic oscillator potential, and then you can do the same sort of a thing. And if you do that sort of a thing, you will find there is only a first order and there will be only one arbitrary function. Because it is second order, you have two arbitrary functions of k sitting there. Now I think this concept of negative energy solutions and positive energy solutions and things going backward in time, forward in time, etc. is some historically very important and physically completely confusing concepts. So I am not going to go into that. These are just solutions to the mode function. Another important reason I am not going to go into that is that the only classical field which we know of, namely electromagnetic field, you will have exactly the same equation component by component for the vector potential, and when you solve this you will write down exactly the same solution, you will have exactly the same kind of expansion, and you will never ever once in classical electrodynamics talk about negative energy solutions. Okay, so the maths remains the same, so physics should remain the same, so there is no need to get into that. So when you read the textbook, just remember, read it through, but keep a pinch of salt with you. Okay, so this is what we have got. Now, how do you determine alpha and beta? You need to tell me what is phi at t is equal to 0, And you should also tell me what is phi dot at t is equal to 0. If you tell me what is phi at t is equal to 0, if I go back and plug into this, I will get a particular combination of this, which I can determine. Then if you give me phi dot as well, I will get another combination from which alpha of k and beta of k can be determined entirely in terms of phi and phi dot at t is equal to 0, and you can evolve it forward in time. Okay. So this is what happens in the case of a free field theory. You can of course go and compute other quantities like what is pi, what is the Hamiltonian, etc. I won't do this, I will throw this into assignments. Okay. So it is interesting to see what kind of concept I'm on. And later on we need to do this again when you quantize the field, so therefore you remember what is happening. One last comment at this level is that suppose you take this expansion and you plug it into the action. You can already guess what it would do, because you have these QKs and in the action you will have a, where is the action? Here it is. No, well I wiped it out. Okay. So the action will have a dA phi dB phi with a GAB acting on it. So you are going to get a phi dot square and a del phi square term. The phi dot square will just be q dot square, and when you integrate over all of them, it will give you the harmonic oscillator for each mode. So the action will turn out to be the sum of the actions for the harmonic oscillator for each mode. Something which we have already seen. These QKs are just the QKs we introduced from the propagator. So there is nothing very surprising which is happening. Fine. So this is all I want to do as far as the free field is concerned. Now let us make life more interesting. We want to study fields in which this potential is not just quadratic. We want to introduce something which I would call unharmonicity. Now the moment you say that it is not quadratic, then the phase space is very large. I can put any v of phi I like. Classically you can put any v of phi. You probably want to keep it positive definite, but you can put any v of phi and study it, and that will be a good classical theory. Much later on when we do renormalization, we will see that in 3+1 dimension there is a limitation on what kind of v of phi's will have meaningful quantum theories. Okay? So I'm not going to get into that right now, but let me think of the simplest kind of v of phi which you can have, and let us explore its physics. It turns out that that physics is rich enough. So if you look at v of phi, we started with a term which was half m square phi square. Let me write this as half mu square phi square for the moment. It will turn out to be useful. Okay? Then I can add terms to this. And the simplest term I can think of adding to this, preserving the symmetry of this, is something which I will call lambda phi 4. We will be spending enormous amount of time with this kind of a model as we go along and when we do the quantum theory. And this is an extraordinarily beautiful system, I mean in spite of its simplicity. So you have a v of phi in which in addition to phi square we have added a lambda phi 4. Yeah.
Why not cubic and linear terms?
Yeah. Cubic and linear terms, if I change phi to minus phi, will become negative. As a result of which the Hamiltonian won't be bounded from there. So we want bounded Hamiltonian. So we would like to keep to even orders. Anything beyond phi 6 etc. has problems with renormalizability. But that does not mean it should be a polynomial. You can add a cosine of alpha phi, and those models are studied. But they all have problems in quantum theory, so I am going to stick with it. But the main reason is that the amount of beautiful things which come from just this potential is so nice that it is good to maintain the simplicity and still get that. Okay? So that is what I am going to do. Okay, so you have a v of phi which is like this. Now you want to study what is going to happen. And the first thing which you realize is that if you write down the field equation, you cannot solve it because you have a phi cubed here. And nobody knows what is the general solution where there is a phi cubed on the right hand side. Okay. So if you want to study it, there are techniques. Like you can think of this as some small correction to this and do perturbation theory, etc. etc. And many of this which we will be doing. But I want to concentrate on particular example. So if both mu square is positive and lambda is positive, then you end up getting a theory in which the free field theory is perturbed by this lambda phi 4. with a positive lambda. So what does it do? The free field theory has some particles with some mass, and lambda phi 4 introduces interaction between these particles. Okay. Now this interaction actually turns out to be repulsive, and there are ways of showing that. I'll probably put it in as a problem in the problem set. It's not, it introduces an interesting trick, but except for that it is not very illuminating. So just take my word that this lambda with a positive lambda, this produces a repulsive interaction among the particles of the free field theory. But that is not what we are going to do. What we are going to do is to take advantage of the fact that the lambda phi 4 dominates over m square phi square for large phi. As a result of which, I am now allowed to flip the sign of this, and I can study models like this, where this has a minus. Now the moment I have done that, I cannot interpret this as my mass of the particle at all. Okay? But I don't want to, and I don't have to, and I want to study the structure of this thing. And as I said, rest of the lecture is singing in praise of this particular model. Okay? So let me try to explain a few features on this. The results of this model depends on the dimension in which you are working in, the spatial dimension. And the simplest case which you can study is zero spatial dimension. What is a zero spatial dimension? Zero spatial dimensions means all the space dependent terms are gone. So that is quantum mechanics. It is 0 plus 1 has only a harmonic oscillator kind of a term there. And the potential which is drawn here has this characteristic double well shape. So what you will have, okay, let me draw it like this for the moment and then we will change it. Okay, the way I have written it down, like phi is equal to 0, b is 0. This is b and this is phi. Okay, but what we would like to do is to shift the axis. That is, add the minimum of this so that we measure everything from here, so that the lowest and the state has 0 energy. So this is quantum mechanics in this potential, double well potential, and I am sure you have done it in a course. The important point about this is that the potential is symmetric about the origin. So phi goes to minus phi is an invariance of the theory. Normally you would have thought that the ground state can be here or here, but in quantum mechanics tunneling is allowed. So if you take that Hamiltonian, you will find that the amplitude for it to go from a state peak from here to here is non-zero. And you can in fact compute it using path integrals, etc. And you get an exponentially suppressed by this potential help, there is a tunneling amplitude. That means there is the degeneracy will be lifted. You will get one symmetric state, which is a symmetric combination of this, and one anti-symmetric state, and you will find that the degeneracy is lifted. There is a genuine ground state, and everything can be done about it. Okay? This is very interesting, but we are not going to do quantum mechanics, so we will leave that aside. Now let us look at the situation in field theory, where you have at least one spatial dimension. It doesn't matter how many you have, 1, 2, 3, we are interested in 3 plus 1, but let us take at least one spatial dimension. The important thing there is that you can no longer have tunneling between these two states. That is because when you compute any tunneling amplitude, suppose you take a state where the field is a constant here or a field is a constant here, and if you think of it as a tunneling as given by some kind of a WKB or an Euclidean action, it will be integrated by the spatial volume. That is, you take the action for that configuration and you integrate it over spatial volume. And the moment you have space dimensions coming in, the spatial volume is always infinite. As a result of it, the tunneling amplitude is 0. So you now have genuine degenerate vector. It can be here or it can be here. Okay. Now this is the part which makes it extraordinarily beautiful. You can have now solutions to this theory in which, for example, asymptotically it goes from here to here. Now this is again very interesting physics in classical field theory. These are such solutions are called solitons, but I am not going to delve into that. What one wants to study here is that you want to have a configuration, a field configuration, which is of the following form. There is one spatial dimension, and this is phi. You think of a field which varies like this. In fact, the solution happens to be tangent. in one dimension static solution, you can integrate this. You take this, okay, I never wrote down that equation. Okay, let me write it down first. So this is phi double dot minus del square phi is equal to minus v prime of phi. Okay? And if it is static, only this del square is going to contribute, and there is one dimension, so it is d square phi by dx square, and then on the right hand side you have a phi dependent v. So the problem is reduced to quadrature, it is classical mechanics. And in the particular case, you can actually integrate it and you can get a solution like this. It will vary over some length scale L, which is determined by the scale, the two parameters in the problem. If you look at the energy of this system, which is by taking the Hamiltonian and computing it, you will find that the energy is essentially concentrated on this region. That is understandable because energy has a d phi by dx the whole square that vanishes when this goes flat. The energy also has something which is phi square minus the vacuum expectation value square, because the moment you have this, I can rewrite this as, let me write it as some 1/4 lambda phi square minus v square the whole square, where v is this. This is minus v. Why is this true? If I square it, I get lambda phi 4 all right. Then I have one free parameter. So minus 2 phi square v square can be, this v can be used to match with this minus phi square. Then I get a constant which I ignore because I can add a constant to the potential. So if I write it like this, the phi actually goes to plus v here and minus v here. This is how the solution looks like. So in this range, the potential energy term contributes nothing and the kinetic energy term also doesn't contribute. As a result of it, you have a kink-like solution. So you have, and the entire theory is Lorentz invariant. So you take it as a static and boost it, you can have a kink which is moving. So it is almost like a concentration of energy which is moving in space, which is extremely nice. So these are called solitons, and they were first observed in fluid dynamic phenomena, and then in field theory it has been used, etc. Unfortunately, we don't have time to study any of this, but you can work everything out in this case. It will be lovely if we had such solutions in 3+1. So can we have a potential like this in a 3+1 space-time where you have an isolated kink of a particle which is moving? That would be great. Then it will be a model for elementary particles built out of condensator fields, etc., etc. Then there is a spoil sport called Derrick who came along and proved a theorem that such solutions cannot exist. Okay, so anywhere beyond dimension 1, you do not have solution to a scalar field theory with arbitrarily complicated potential with some conditions which I will just now write down, such that it has finite energy and is completely static. Okay, this one, whatever I wrote down as a soliton in one dimension doesn't generalize to 2 and 3 dimension. So the proof of it goes like this. Let us look at the energy and try to minimize it for a static configuration. So that would be a solution if we can do that. So the energy is written as some integral over ddx over this space of one term which will essentially be half gradient of phi in d dimension square, which is the sort of kinetic energy term. Then you will have another term which is integral over dd of x of some potential energy which I will call some v of phi. Without any loss of generality, I can assume that the 0 of v is at the ground state, the minimum of v is at 0. So this is a positive definite integral. This is also a positive definite integral, and we are interested in finding a solution where both these quantities are finite, so that the total is finite, and it is completely static, which has already gone. Okay, we want to do that. Now suppose you have such a solution. Okay. Then it is a solution in which the energy is minimized, and you have got a configuration which is phi is equal to phi of x. What I am going to do is to change this x to lambda times x. This is like varying the solution. That is, I think of a new function phi of x obtained by taking the old solution and changing x to lambda x, and whatever I get is my new function. But since it is a minimum, if I do that, it should be minimized with respect to lambda as well. It should be a minimum with respect to lambda as well when lambda is equal to 1. Right? That is the game we are going to play. So what this will go into is that, suppose I change x to lambda times x. We ask how these two terms are going to scale. So here, if I change x to lambda times x, I want to get back the same thing. So I have changed x to lambda times x, and then I am going to put a lambda at the denominator. So I get lambda to the power minus. Okay. So let me do it this way. I put a lambda here, and then I put a lambda to the power d at the denominator. So I get a lambda to the power minus d. Then by the same token, this will give me a plus 2. Because there is a d by dx in the denominator. So essentially the argument is this is d minus 2 in the length scale. Times whatever was the original quantity. Let me call this original quantity as E kinetic. The kinetic energy term, which is of course an abuse of language, but let us call it the kinetic energy term. Then you take this and ask what this is going to do. So here I am just going to get whatever I got from here, that is lambda to the power minus d times E potential energy term. Okay. Now let us consider the minimum of this, dE by d lambda at lambda equals 1, and we want to be equal to 0. So if I differentiate this with respect to lambda, I first get here 2 minus d into lambda of something, but lambda is equal to 1, so that doesn't matter, times E kinetic minus d E potential. Okay, this quantity should be 0. This tells me that 2 minus d, assuming I did all the maths right, E kinetic should be equal to d times E potential. Right hand side is a positive semi-definite quantity, and in fact it is a positive definite quantity because it is an integral over potential. The potential has the minimum at 0. Okay, so assume that the potential is non-trivial and the configuration proves at least a little bit of non-zero potential, then this integral is positive. So the right hand side is always positive, so left hand side has to be positive. This is already positive, that tells you the solid. So anything beyond that, you cannot do that. In particular, if d is equal to 3, you get a manifest nonsense with a positive quantity being equated to a negative quantity. So in real 3 dimension, building elementary particles out of solidonic like excitations with just a scalar field, you cannot do. Okay? So that is bad, but as I said, there are other very beautiful things which happen with that potential, which I want to describe. So we may overshoot a little bit today because I don't want to stop this halfway through. But there is nothing happening into MRC paper track or something. Alright. So in order to describe this in the most general context, we want to change gears at this stage. Let us not do this lofty quantum field theory, but do some very mundane thing, condensed matter physics. Take ferromagnet. Now, what is the interesting thing about ferromagnet? Experiments prove that the ferromagnet is some kind of an object where you have a transition temperature. There is a critical temperature above which there is no magnetic order, and as you cool the system below a critical temperature, suddenly a magnetization develops. So in fact, if you plot the magnetization versus the temperature, it has a behavior something like this. This is Tc. And the behavior is cuspy. That is, it goes as T minus Tc to the power a fraction. Okay. Now the cuspy functions are non-analytic, and we hate non-analytic functions. They produce branch cuts and all kinds of bad things in the complex plane. Now the question is, how do you get something like this as a function of behavior in temperature? Starting from sensible statistical mechanics, where the partition function is obtained by summing over e to the minus energy I upon kT. The partition function has a nice analytic behavior in T, and if you look at the grand partition function as a function of whatever z to the power n in which you are summing up, some very general theorems can be proved showing that phase transitions can never occur in statistical mechanics. So these theorems were actually proved. Okay? Of course, right before your eyes, people are seeing ferromagnets. So the question was, how do you describe this? Now, the first part of it, the mathematical issues are fairly easy to sort out. I mean, it has to do with, for example, things like adding infinite sums versus finite sums. Suppose you take 1 plus z square plus z cubed. To finite order arbitrarily large, this has no pole anywhere. You sum to infinity, it is 1 over 1 minus z, which has a polar z is equal to 1. So things can be different based on that. So that is not a real worry, but you have to come up with a description. How do you find this? There was also another thing which was noticed, that the magnetic susceptibility of this material diverges as T goes to Tc, essentially as again a power law. You can think of it as 1 over T minus Tc. Now, how do you describe such phenomena, at least phenomenologically? Now, if you think about this, there is something very peculiar going on here. Normally, when we think of symmetry and broken symmetry and order and disorder, we sort of associate symmetry with order and asymmetry with disorder. I mean, that's the conventional newspaper parlance. Okay? But it is exactly opposite in physics. If you think of a system at high temperature, the ferromagnetic system at high temperature, if you think of them as some internal magnetizations with vectors, they are oriented in all possible directions. This is the disordered state. But disordered state is the symmetric state. Because if it is completely disordered, when you rotate it around, all directions are equally well covered. Now when you go to the ordered state, the symmetry gets broken because a particular direction is taken into account, and you have only a residual symmetry about that axis, but not a complete symmetry. So you start from a phase which is symmetric to a phase which is broken symmetry. So there is some symmetry in the original system which gets broken below the critical temperature. Now how do you break a symmetry and how do you introduce a symmetry? Introducing a symmetry is very easy. You write down the microscopic system in such a way that it is symmetric under whatever transformations you are interested in. You can do that. So you can write down a microscopic Hamiltonian for the ferromagnet, which is perfectly symmetric. But then you are stuck. The only other parameter you have got is the temperature, right? Now how do you fool around with the temperature such that the system has asymmetries thrown in? The most elementary way you break a symmetry is add something to the Lagrangian, which breaks the symmetry. But that route is blocked for you here. Because you want the same thing to be, you don't want to touch the Lagrangian or the Hamiltonian, because we want the underlying theory to have the symmetry. But yet, the manifestation of that, when you look at it, has to be asymmetry. Here, two people, in particular Landau, the other guy is Ginsberg, came up with an absolute brilliance. What I said was, let us try to describe the entire thing phenomenologically. So this is a very general theory of phase transitions and critical phenomena. But I will use this magnetization as a kind of a toy example. So let us think in terms of magnetization, which is a vector, but that need not scare you. So let us consider something like a potential. Actually happens to be free energy, but something like a potential which is a function of the magnetization. Okay, and let us write down an expression for it. So let us say he wants to write the expression which is of the following form: some A which could depend on the temperature, some coefficient times m square. That looks nice. It maintains all the symmetries of the theory. So this is the vector square. Then let us put a B which depends on the temperature, and let us again maintain the symmetry. We don't want any odd terms, M4 plus etc. Very innocuous thing. Then his genius was to say that let us assume A vanishes at the critical temperature. The A of t as a function vanishes at the critical temperature, but B of t has a smooth behavior. In fact, we will think of B as constant for our purpose near the critical temperature. Okay? So if A is going to vanish near the critical temperature, then near the critical temperature I can think of this as being approximated as some alpha T minus Tc m square plus B m4. Okay? Nothing is discontinuous, nothing breaks this symmetry, and nothing is non-analytic. This is the as analytic as you can get. It's linear in T minus Tc. But see what has happened. Let us plot this. If you plot this function, which is V as a function of m, for t greater than Tc, this is positive and this is positive. So the minimum is going to be at the origin. And the system will sit here. There is no residual magnetization. Okay, the system will have zero magnetization and it is at t greater than Tc. Now you lower it, at t is equal to Tc, it is still this shape broadly, except for phi 4. You lower it below t equal to Tc, it goes over to this picture. Because the sign of that m square flips. So for t less than Tc, you are going to have a system whose potential is going to be like this. This is the beauty. So the minimum of the potential, if I just differentiate this with respect to m, I have 2 alpha T minus Tc m plus 4b m cube is equal to 0. It has two solutions. Either m is equal to 0, which we are not interested in. The other solution is going to be m square from this is equal to minus m and m I have cancelled out, so m square is equal to minus 2 alpha T minus Tc upon 4b. If t is greater than Tc, you cannot use this solution because it is m square being negative, it cannot happen. So you have to pick the other solution. So t greater than Tc, it sits here. For t less than Tc, this is negative, and as a result of which, you are going to get a magnetization here. That's it. So you start with a Hamiltonian which is perfectly symmetric under m2 minus m. The ground state breaks that symmetry. This is why we call it spontaneous symmetry breaking. So the fact that in quantum theory it is not just the Hamiltonian or just the action, but there is something else, the states in the Hilbert space, is what is being made use of in some sense. The state which you choose breaks the symmetry, but not the Hamiltonian. So the symmetry is preserved at the Hamiltonian, both for t greater than Tc and t less than Tc. M goes to minus m is a symmetry for any value of it. But the ground state now breaks the symmetry between these two and picks up something. Okay. Now this is beautiful enough, and that you can have systems in which the symmetry is broken right before your eyes, because the minimum shifts to a non-trivial value. But things get better. Suppose you have something like this and you want to study how this system is responding to an external magnetic field. So that is how you get susceptibility and things like that, right? So let us first take the high temperature phase where everything is fine, and we want to add to this. So let me write down the full Hamiltonian for this system or a Lagrangian for this system. So what you want to do is to think of a Hamiltonian, let us say, where you start with a half d alpha of m dot d alpha of m. This is like the kinetic energy term in the Hamiltonian. Then you want to add to it its potential V of n. And you can also add to it external magnetic field, let us say H dot n. Okay, I will choose the sign of this in order to have a right behavior. I don't remember whether it's plus or minus, but it doesn't matter. You add an external potential. And then you ask how the system is going to behave. So you want to minimize this. So you write down the equation for m in terms of that H. So if you do that, what you will essentially end up getting is that, think of this as something like the square of the mass. So you know that you do this variation, you will end up getting minus del square of this m plus a, which comes from this, times m is equal to h of m. Okay? Yeah, this probably should be minus h. You decide on that sign. So essentially, h, whether it is h or minus h, it doesn't matter. So when you differentiate with respect to m, you will get a h. So what have we done? We are studying the response of this particular system with this kind of phenomenological potential energy to an externally applied magnetic field. Okay? So this is something which we have done millions of times. If I think of this as something like m square, this is just our standard Klein-Gordon equation, because if I add a d square by dt square, this is just going to become something which we wrote down just now. Okay? So what are the solutions to this? The solutions to this are very simple. Again, you go to the Fourier space and evaluate them. But we had done this when we studied Yukawa potential, because when you had a static source on the right hand side. The solution will be given by this magnetization m at any point x will be essentially integral over d3y times the externally applied h at some point y times a Green's function. And the Green's function is the Green's function of this theory, and that will be 1 over 4 pi 1 upon x minus y times an exponential minus, if this has been m square, you would have got m. So now you will get square root of that. Square root of a into x minus 1. This I am going to leave to you to do, but this should be obvious. Okay, so this is essentially the Yukawa potential kind of calculation we are doing, scalar field in the static limit, which we had already worked out, and we have shown that the Green's function is essentially exponential minus of this upon 1 by x minus 1. Okay, now there are various things here. Firstly, what is it telling you? It is telling you that if you put a magnetic field outside at a point y, and I look at what the magnetization it has produced at a point x, there is an exponential suppression of the influence of h on it. So there is a scale length which is coming in here. So the scale length L of the system, let me call it psi, which is what condensed matter will call it, is essentially 1 upon square root of a. That, if you look at the form of a, is essentially proportional to 1 upon square root of t minus t. So the correlation length between your perturbation and the response, the characteristic length scale over which this phenomena takes place, varies with temperature, non-analytically, and also as 1 upon square root of T minus Tc. As you approach the critical temperature, the correlation length becomes infinite. So the system which had only short range order, that is, if I perturb it here, its response is only felt in an exponentially damped way over a length scale, exhibit as though it has long range order at the critical point when T goes to Tc. Okay, this is the first thing which you find from here. The second thing you find is that you can also calculate what is the susceptibility. There are various ways of doing it. The simple trick is to assume H is a constant. Suppose I put a constant magnetic field and I get a constant magnetization. I want to know what is the proportionality. That will give me chi. So if H is a constant, I can do the integral there. So for a constant H, what I will get is capital M is equal to capital H times integral over, that variable can be shifted, d3y 1 upon 4 pi 1 upon modulus of y e to the minus y by the correlation length psi. Right? That is what I have. So take this as y square dy, so root infinity proportional to 4 pi goes away, 1 pi y goes away, this is y dy. So put a psi square here and you put a psi square here. Okay, this is a pure number because I can scale everything out. So I get m is equal to, m is proportional to h psi square into some integral 0 to infinity mu d mu e to the minus mu, which you can work out. All the temperature dependence is contained in this. So the chi is the proportionality constant between these two, and that chi is going to be proportional to psi square. Psi square is 1 over T minus T. That's exactly what you want. The magnetic susceptibility diverges at T is equal to T. So all the phenomena which you have been sort of, this is not a course in condensed matter physics, so I'm going to stop here. But the basic idea is that if you write down a phenomenological object like this, because of this spontaneous symmetry breaking, it can explain the host of phenomena which is unexplainable from some microscopic theory. Now the microscopic theory's task is reduced to starting from there and getting an effective potential of this kind with this kind of a temperature dependent. All we want is A of t to have a linear behavior near that temperature and B to remain constant at that temperature. Then all the phenomenological thing can be discovered. And all this was possible because the ground state breaks the symmetry of the system. Okay? So this spontaneous symmetry breaking, it turns out, is a great unifying concept in physics. And all the way from condensed matter physics to particle physics, the entire Salam-Weinberg model for electroweak unification would not work except for this phenomenon. So which we are going to study. So we are going to take it step by step. So our next task would be to study this system exactly like this. The moment you have got this, there is this, the potential can be written in this form in any dimension, and we can no longer think of this mu as a mass that we already see. So what is the mass of the excitations? How does it behave? And that is what we will do next. And this is with a single scalar field. And it turns out that the life becomes more interesting if it is a complex scalar field, if it is two-dimensional. And it becomes still more exciting if you have an electromagnetic potential also added. So that is what we will do in the next couple of lectures. Questions?
So here, where are we assuming that T is greater than Tc? In this entire argument.
Oh, otherwise you won't get exponential. That exponential is valid because it has a square root of A.
Right, so I'm just...
If T is greater than Tc, then you get the square root of A.
Okay.
Right? Otherwise things blow up and stuff like that. The solution has some boundary conditions which has been imposed because that is all valid only when A is positive.
And in the previous step, so how do you know beforehand that alpha will be positive? Because otherwise symmetry will break at high temperature rather than...
Exactly.
So how do you know?
No, that is why it is phenomenological. So there is a phenomenological theory for the phase transition is what is being developed here. What you say is that let us assume the fundamental theory is such that the effective behavior in terms of some effective variables, which is called the order parameter, and there is a potential in terms of the order parameter, and let us assume that that potential has a particular form with certain properties. So the properties is that this is going to be of this type with alpha positive, and this is going to be, this also is important, right? If this also has a T minus Tc behavior, then you are sunk. You don't want that. So this is analytic around T is equal to Tc.
So to make a point that there is a effect, of course, T.Padmanabhan also applies to superconductivity in very,
Yes.
very similar spirit.
Yeah, I'm going to do that because the moment I have a gauge field mu added to it,
Okay.
I will get London equation out of it
Yeah.
and the skin depth. Yeah.
And also something like P-part coherence.
Yes, that I don't think I'll have time to do.
Electrodynamics will
Yeah.
be emerging up. Also discussing later on, like in the immediate future probably, Boson and Higgs model also can be discussed.
Yeah, Higgs I will mention later on, but I'm going to do superconductivity, at least rudimentary idea of superconductivity the moment I have a vector potential in. That much I will do. Yeah.
I'm just wondering chronologically which came in first, because superconductivity also has this property that expectation value, the order parameter, is came first or?
No, the superfluidity came first.
Okay.
Okay, because the problem with superconductivity was that writing the ground state wave function was a fairly tough job. Right? I mean, PCS has to come. It was one of the longest gaps between theory and experimental detection. The PCS, yeah.
And you were mentioning that 5-4 theory is repulsive, but I thought in a previous lecture I didn't understand it properly at that time also. You were saying that scalar field theory will always
No. What I said was, if I have a m square phi square theory, and that m square phi square theory is coupled to some jfx, the self energy of that jfx will give you attraction.
Right.
That was the exchange of a scalar particle will lead to attraction. Exchange of a vector particle will lead to repulsion. Exchange of a spin 2 particle will again lead to attraction. This is different. This is a self-interacting scalar field theory.
When you give a physical picture, like when you don't have the temperature is above Tc, everything is disordered, so there is no preferred direction. But below Tc, you have preferred direction.
Okay.
But the potential which you wrote, there only the ground value is actually
So
switching, but there is no
what you are going to, well, as I said, this is the issue with phenomenological models. What you have to do is that you have to first understand that there is a magnetization which is produced. Okay. Now, if you go into the details, what will happen is that there will be domain structures, and in each domain structure, you have to have some particular value of m. You need a non-zero value of m. I mean, you cannot have m cancelling out everywhere and producing a modulus of m which is non-zero. Okay. So that is how it happened. The real life is much more complicated. You have to worry about the domains, their interfaces, etc. But what it gets you is that you can have the same Hamiltonian with just this behavior. Gets you is that you can have the same Hamiltonian with just this behavior, which will give you non-zero magnetization in the ground state. When you go below T is equal to Tc.
So the angular dependence never comes in the.
That doesn't come in this. I mean, you will not be able to tell me that if I take a disordered ferromagnet and I cool it at this particular point, whether it is going to point in this direction or in this direction.
So the magnitude of m actually tells us that there is a preferred direction. That's
Exactly.
When you were talking about this tunneling part,
Right.
so when you talk about dimensions, how the tunneling probably
Right.
goes down, can you
Right.
repeat that once?
Okay, so one way of doing this is with path integrals, which I mentioned earlier on, but I didn't do in full detail. The tunneling amplitude is essentially going to be e to the minus the Euclidean action for a particular classical field configuration. This is how the tunneling amplitude will go. Where this field configuration has to be chosen such that at t is equal to minus infinity it is at one place and t is equal to plus infinity it goes there. Now this is doable because the moment you go to the Euclidean picture, the potential reverses sign, right? So as a result of which, in the Euclidean case, when I look at it in the Euclidean, the potential has a form like this. So you can have it is like a classical mechanics with this potential. So you can have a solution where a particle starts from here and rolls down and reaches here at infinitely later. So you can compute that. But if you take any one of these minima and put some value for that, I mean this is the general picture of tunneling. And if it is in quantum mechanics, it is all perfectly fine. You can have this potential calculated and all. But when you do this in quantum field theory, this action will always involve an integral over d3x or d2x or dx or whatever. There is a spatial integration there. And when phi is independent of x, that spatial integration will give you a divergent quantity as an infinity. So the tunneling amplitude will go to 0. So quantum mechanics is very different from quantum field theory with a double well potential because of this reason. In quantum mechanics, there is actually the ground state are not degenerate. We know that because there is a tunneling across and the ground state degeneracy is lifted and there is a symmetric state and an antisymmetric state. This I am sure you would have done in quantum mechanics code. I mean you can't solve that problem exactly, but there are some complicated functions in terms of which Schrodinger equation can be written, solution to a Schrodinger equation can be written down. And you can compute what are the two energies, their difference, etc. Okay? While when you do it in field theory, these two vacua are strictly degenerate. There is no tunneling amplitude between these two vacua. Any other? Okay.